Right. Welcome, everyone, to the ICTS Colloquium. It's a great pleasure to have Vijay Natarajan from the Indian Institute of Science. Vijay is a professor in the Computer Science and Automation department. He got his PhD from Duke University, and prior to that, he has degrees in computer science and mathematics from BITS, Pilani. So his interests are computational topology, computational geometry, and some data visualization. So he's going to be talking about topological descriptors and scalar field comparisons. Thanks, Vijay.
Thank you, Vishal, for inviting me. Thanks, everyone, for coming in on this afternoon. Let me start with a disclaimer. I'm a computer scientist. I know there are mathematicians and physicists here. So this talk is going to be about how we use topology and some tools to solve some interesting problems in data visualization. So hence the title focuses more on the tools that we use, and we will see the end goals and the results during the talk. So like Vishal was saying, so I come from IISc, so where we have a group looking at different problems in data visualization, which refers to the generation of visual representations of data. Towards this, we design techniques that are based on topology-based representations of data. So we design techniques for representing the shape of data, for computing this so-called shape, for comparing different data using this shape-based representations, for ordering and for querying the data, and of course visually displaying the data. And this particular set of tools has kind of been developed over the past 10 to 20 years. It's gained a lot of popularity in the past decade or so, and the applications range from what you see here are kind of instances of our work, from kind of the study of fluids to biology on the right, and everywhere, all other. It touches just multiple disciplines. So let me kind of try to narrow down the focus for the purpose of today's talk. So I will be looking at quote unquote scientific data. So when I say scientific data, I mean data that comes from typical science engineering disciplines, data that has a geometric context. The term scientific data is more historic. People, it doesn't refer to data that is more scientific than other data. This is just a historic kind of naming, so if you bear with me. So essentially data that comes with a geometric context. For example, what you see on the left is, let me use the pointer just for once. From the left towards the right, you see images from different modalities. On the left, what you see is the near infrared image of the breast, where a particular tumor is highlighted. And then on the left bottom, you see an electron microscopy image of a virus, which has a lot of symmetry in its structure. And next, moving towards the right, you see the image from a CT scan of the human torso with certain parts highlighted and certain parts which are difficult to highlight, as we will see in the next few slides. Then moving on to pore networks, the study of materials, and the pores that actually play an important role in its strength and its kind of flexibility and so on. And towards the right, the study of the large-scale structure of the universe in cosmology. So the data here comes from different sources. It could come from imaging modalities, it could come from simulations, or it could come from just sensing devices. In all these cases, like I said, the data comes with a geometric context, which means that we represent the data as a scalar valued function over a Euclidean space. So typically R2 or R3, right? So that is going to be the focus of today's talk. data that is represented as a scalar function or a scalar field, as I will call it. So, like I said, visualization refers to the study of visual representations of data. Classic techniques aim to visualize the data by directly presenting the data to you, either by mapping color or by plotting simple curves such as these isocontours, something we are familiar with, right? So an isocontour, just to set the stage, is the collection of points that have a given scalar value, right? So it's the pre-image of a particular scalar value. This works well in 2D for 2D functions because the pre-image is a contour and you can pretty much describe the entire scalar field by plotting multiple contours. You can imagine that quickly this doesn't work as well in 3D, although it has been found to be useful, but it doesn't work as well because the isosurfaces in 3D can get very complex, right? And understanding them is already a challenge, primarily from the human perception viewpoint. But nevertheless, there are lots of applications of isosurfaces. One of the early applications of isosurfaces has been towards the study of the human anatomy. So in a medical context, where if you, let's say you have a CT scan, then the isosurfaces of some carefully chosen values. So the values here, if you can't read it from far, 30, 80, and 200 happens to correspond to interesting spatial structures. For example, the skin with some noise, and then at 80, you actually get the skin, and at a higher value, which is 200, you get the skeletal structure. So this is the data here is a CT scan. And so the CT scan captures some form of, it's called density, but it's not true density of the material. It's density because it captures so the attenuation of the X-rays is translated into a value. So it essentially captures a characteristic at that particular point. So it's a 3D volume. Right, and high values typically correspond to kind of denser material, not always, but loosely. So moving from surfaces, since we have with us an entire graphics pipeline, thanks to all the graphics cards that come for free with all our desktops and laptops, right? We can actually display very heavy-duty graphics on a simple, even a mobile phone. So, so using those techniques, one can actually display the entire 3D volume using transparency. So here you have the scalar values mapped to both color and transparency. That allows you to see the 3D structure and highlight regions of interest. But this also quickly becomes difficult when the 3D structure is really feature-rich. As you can see from the large-scale structure, this is from the millennial run. I don't know if some of you have worked on this, but yeah. Yeah. Right. So, so you can imagine that you have a 3D scalar field, right? So a 3D scalar field. So in this case, the scalar field is three-dimensional. So at every point in 3D space, I have a scalar value, right? So I design a so-called what's called a transfer function. So this transfer function is a one-parameter function. So it works on the scalar values. And for each scalar value, you identify a opacity or transparency, right? So and then for each scalar value, you also assign a color, right? So for every scalar value, you have a pair, which is a color and transparency. So color could also be described as RGB. So you have RGB and opacity, right? So for example, for regions that correspond to the skull, you would give higher opacity. So you will not be able to see through. Whereas for the scalar values corresponding to the skin, in this particular image, we have assigned lower opacity. So you can kind of see through. And then we have a way of sending this entire volume of color and transparency into our graphics pipeline. The graphics pipeline is able to render this entire scene by shooting rays and kind of collecting the opacity values and the color and giving you an image, right? So this is called ray tracing. So the input scalar field is from the medical image, the CT scan. The two values that are computed are derived or kind of mapped. These are pseudo colors. So I don't call them as scalar fields really, but those are used only to display, only to create the visual, right? So think of it as two steps. You go from the scalar field to this color and transparency, and the color and transparency is composed to generate the final image, right? So the color and transparency is decided by the user, and you can tweak it to highlight certain parts and not kind of remove certain parts. When I talk about scalar field, I often talk about the input, which is your medical image. Right? Yeah, that's a single scalar field. Yes. Yeah. So for today's talk, I focus on single scalar fields. Yes. I will try to kind of use examples to highlight that to you. So let me try to use so I'll try to give a simple example to highlight that in the next slide. Right. So what I mean by feature rich is there are multiple regions of interest to the human, and it's difficult for you to see all of them. Right. It is okay. So there are perception-based studies that kind of tell you that you cannot see more than so many colors, right? So similarly, there are user studies that tell you that you cannot see if there are more than 7 colors. You are not able to distinguish between them. So it is. So in that sense, it is objective, but based on user studies. Yeah, because the human is always in the loop here. Yes. Yeah. Any other clarifying questions? Yeah, please.
So we functionally mapping one scalar numbers. This cannot be subjected. So what I understand is that could I have two different ones which are the same colors but different transparency?
Sure, that's possible. Yeah, but typically we wouldn't do something like that, right? So the function goes from the scalar value to color. Yes. So yeah. So each scalar value gets a unique color, right? So and a unique transparency. Yes. But I think you're asking about does a single color apply to two different scalar fields? That's possible. Right? If you do not care so much about them, then yes, that is possible. Yeah. Right.
But why do we need two attributes? So you could have just done transparency, right? Or just color.
Yes. So then I get a grayscale. So I think all of us are familiar with color maps on 2D, right? So if I just give a single transparency and just no color, right? So which means, let's say, white. Or gray or something, right? Then I get essentially grayscale, which is good, which is also useful. But color allows us to highlight. For example, in this case, it allows us to highlight the skin different from the bone, right? So we do not use all colors. So in fact, there are fundamental studies in visualization that say that you do not want to use multiple hues. So often these images, you will notice that they will have 2 or 3 hues, not too many, right? But yes. It is a display parameter. Yes. Yeah. It is only a display parameter. That's what I was trying to explain earlier. Yeah. Yeah. Thanks. But thanks for that clarifying question. Yeah. So the current challenge is not so much on the display. I think I was trying to make the point that if you try to display everything, then it is difficult to try to make sense out of the data. What you would like is some kind of a feature-aware displays, which allows you to identify the features that may be of interest and then highlight them using abstract representations. So why so? Because one, the data sizes increase. I don't have to really kind of motivate this. The data, like I said earlier, becomes feature rich. So here, what I mean is that the number of regions of interest, the number of characteristics that we have that are of interest to the user explodes, and then it becomes difficult to display all of them, right? Again, one example of large sizes is from the cosmology simulation. There are many instances where this you see this phenomenon. So naturally, we have data which is no longer static. We have time varying data which is increasingly becoming common. Simulations are no longer single run; they are often ensemble, and one would like to see the entire ensemble. So this is again significantly increases both the size and the kind of queries you would like to pose on your data, right? The approach that we follow is one where we kind of marry data analysis techniques with the display and the visualization techniques, right? So we would like to create visual abstractions of features that could potentially be of interest, while staying data kind of application agnostic, right? So the visual abstractions that we talk about do not immediately focus on one particular application. They are, in my case, based on topology. They look at topological structures, and we try to display these visual abstractions, and hopefully that helps the user understand patterns or features in the data. Let me give a very simple example. This is not really a running example just for this slide because to set the stage. We remember the CT scan that I showed earlier. What I would ideally like is the image in the middle, right? The one that highlights, for example, some parts of the bone structure, the lungs, and the colon, right? While hiding the blood vessel structures, the tissue, and the muscles, and so on, right? So how do I do that? You really need some kind of a sophisticated UI, right? To put it simply. What we provide on the right is that sophisticated UI, right? So the tree structure you see on the right is called the contour tree. I'll try to define that during this talk. The contour tree captures features of interest. I'll try to define the feature also more formally soon. But in this particular application, a feature is an organ or an individual rib, right? So in connected components of the human kind of anatomy. So that is what I mean as a feature in this particular application. In each arc in the contour tree represents one of these features of interest, right? And quickly you can see that depending on whether the person here is an orthopedic or somebody who studies the pulmonologist, they would be interested in specific regions of interest. They may want to highlight certain parts and kind of hide the others. The tree allows you to now specify which parts you would like to highlight and which you would like to kind of ignore, right? Interactively. And you notice that some of the arcs in the tree are actually highlighted. Those correspond to the regions that are actually highlighted in the middle picture. The ones corresponding to the lung and the colon. And here different colors are associated with each arc. So different transfer function, the one that I introduced earlier, so that you can kind of talk about this. So here I moved from the data to the visual abstraction, which is that tree. I haven't defined the tree yet, by the way. And I've gone to the next step also in developing a visualization tool or a technique for highlighting regions of interest using this abstraction, right? So that's the entire workflow. I will focus more on the visual abstraction for this talk. I will not really talk about the design of visualization systems in this talk, right? Okay, so that was just meant to be kind of an introduction of what to expect, right? What do I mean by topology? What do I mean by topological structure? And how does it play a role in visualization? Right? Yes.
For the abstraction depends on the original image, or it's an algorithm that you can apply on any.
It works on any scalar field, so any image in that sense. Yeah. Yes. Yeah. It works across all applications. Yeah. Which is why it's crucial for us to abstract away details about the application and say that what I have is a real valued function, let's say over R3. And my algorithm works on that. Right? Yeah. Okay, so many may already know topology, but let me just clarify that what I mean by topology. So this is for those who don't know, even though it's oft repeated, I still find that this is very perceptive, kind of an example to say what is topology, right? At least for my work, the fact that you cannot distinguish between the coffee cup and the donut is so crucial, because that is really what we care about. We care about invariants and how to compute them and what are good invariants and right, so on. So of course, there are different ways to capture invariants, starting from the origins of topology, which comes from Euler, right? Looking at Euler characteristic, that's one number telling you something about a space. So I'm not sure how many have done a formal course in topology. Can just okay. So then maybe it makes sense for me to talk about it. So okay, thanks. So topology is about the study of the space and how it's connected, right? So which is why I said a topologist is somebody who doesn't care whether you give her a coffee cup or a donut, right? It's the same, because one can be kind of deformed into the other, right? So what do I care about if I'm looking at the topology of a space? I care about how it is connected, and how do I capture that connectivity? So I capture it via some invariants. So a simple invariant is called the Euler characteristic. You may have seen this in graphs, the Euler number, right? And this works for example, any triangulated space. It's easy to compute for a triangulated space. It's defined for topological spaces. Number of connected components, that's a good way to say if two spaces are connected the same way or the other, right? The number of holes or tunnels. You give me a sphere, you give me a tube. They are connected differently because one has a tunnel and the other doesn't have, right? Voids, empty regions that are enclosed by your space, right? So the different ways to capture the invariants. There are some nice group structures and vector spaces that help you capture these invariants and kind of compute with them. One is called the homology groups, right? So this is something that is extensively being used for capturing kind of the topology of a particular space by representing it using its homology groups, right? So I'm not going to talk much about homology groups, but for those who know about homology groups, this is something that you can keep at the back of your head, right? Okay. So topological data analysis kind of builds on all these invariants that are available in topology, which were always studied, but they were never studied from a computational lens. So one of the early in the early days of topological data analysis, people focused on computing these invariants, right? But what is TDA? TDA is using these invariants together with some geometric tools for understanding your data, right? Via abstract representations. This is a kind of a growing field. It has been extensively used for different applications, as we will see. So naturally, a focus here is on algorithms. How do I compute these invariants? How do I store them, right? How do I compare them? We will talk much about comparison today. And then how do I query, right? If I give you a query, are there other structures that are similar, right? How do I query? And then use that to understand my data. So this is often used together with visualization, and in the past several years, thanks to a few very popular research groups and one or two successful companies, and the growing interest in ML, there has been a nice marriage between topological data analysis and statistical learning. Right? It's highly interdisciplinary, as you can expect. So I'm just coming back from a workshop last week where we had mathematicians who kind of did high-dimensional topology all their life, and then there were these. There was one biologist who has actually done like work on the bench, and several computer scientists. So it's a highly interdisciplinary field. We try to learn each other's languages and kind of come up with new techniques. The applications are enormous. This is just a small list. I will focus on one or two applications today towards the end. Right. So I said the key to topological analysis is these invariants, topological structures, as I will call it, or descriptors. I will focus only on one so that we kind of understand at least that one structure well. And it is going to be that tree that we saw in the example earlier, right? So in fact, I'm not even going to talk about the tree that I showed. It's a simpler version. It's called the merge tree, right? So let's just define this merge tree and then see how it captures features in my data. But any questions meanwhile? Before we jump into the definition, yeah.
Whatever you say, have some general lessons about how to detect data on our.
That's interesting. Yes, not in this talk, but some of, for example, the merge tree has been used for higher dimensions extensively because of the simplicity of its structure. But I can talk after the lecture today, right? Yeah. Okay, so the merge tree is defined as follows. We have a scalar function, yes? So let's call it f, and I'm interested in tracing the evolution of the topology. So here, for those of you who know, I'm just looking at the connected components, just zero homology, right? Nothing else. I'm looking at the evolution of the connectivity of the sub-level set. So f inverse negative infinity up to, I don't know what I call it, C, right? So let's look at a picture. So what you see here is F mapped to color, blue to red, low to high values. So this is the typical color map that we use. So just two hues to go back to the earlier discussion. But this is a simple 2D function, which is mapped both to color and to height, just to kind of highlight the function. And you also see contours. Right, but what you see during the sweep bottom to top is the sub-level sets, which is shown in black. Right. So let's when the animation starts again, you will see that the topology of the sub-level set changes as you keep sweeping up. So initially you have kind of an empty sub-level set, and then as you hit the first minimum, you have one component. Right? We are right now counting just the number of connected components. As you hit the first minimum, one component. The second minimum, when you hit, you have two components. These two merge. Right? It's like filling water into a kind of a terrain, right? And you kind of notice where they merge and what happens when do you have new components at local minima? Where do they merge? They merge at these saddles, right? Passes, if you will, right? And they never die, right? Because they only merge and keep going up. So the one component that was born at the global minimum, it continues, right, and goes on till infinity, right? So this structure is this merging structure is captured in a tree, right? So the tree here on the left, on the middle actually, it captures that merging behavior. So nodes of this tree are minima. That's where the new components are born. The interior nodes are the saddles, the second type of criticality. And there is a global maximum where you just terminate. So that's also added as a part of the tree, right? So it's a very simple tree. You can think of it as a rooted tree at the global maximum, right? And the minima are the leaves, right? So this tree is called the merge tree. Yeah, you had a question. Sure. So the merging behavior of the sub-level sets, that tells us, right? So each sub-level set component is born at a particular minimum. So you can tag it with that particular minimum, right? Who created it. So there is a creator for every component. And when two components merge, right? The two components creators will have arcs coming from them and they will merge at the saddle. So it's a natural Okay, let's see. So E and H. Yeah, so there is a component that was born at C, right? That comes here, and the component that was born at A and B, it merged at E. So now that component belonged to E, right? And it kept growing, and it merged with another component, right? As it went higher up, right? Yeah. Say that again, please. Okay, so these two, so only one of them is a node. I just retain the labels because they appear in the other figure. So these are just labels. There is only one node here in the tree. Right? These are just labels. N is the global maximum. Yes, yeah. You do pass M, but nothing interesting happens there. Why is? Okay, so it's a field on a finite, yeah, it's a scalar function on a finite domain. Oh, this is a finite, finite domain, yeah. A good point. I'm coming to that in the next few slides. When I talk about, right, yeah, when I talk about identifying the critical points and, yes. Yes, you've just jumped 2 slides ahead of me. Great, yeah, thanks. So before going to that comment about like why do I know these are the critical points and so on, let's see that the whole behavior is similar when I look at the super level sets, right? So when I do the sweep from top down, I don't show it in the animation here, but you can imagine sweeping down and you get the global max, the local maxima, and then they keep merging till you hit the global minimum, which is A. Right? So these are the 2 trees, both are called merge trees, depending on the sweep direction. And the 2 trees can be put together into this tree, which is called the contour tree. I will be focusing only on merge trees today. The contour tree is what we saw in the earlier picture with the medical example. Right? Okay. So a few points here before we jump. There was a question about merging behavior. So that's actually important. Every component here, the components are my features. Here, from here on, when I say feature, I mean topological feature, and I mean sublevel set components, right? In a different talk, this could be something else. So sublevel set components are born at local minima. So there is a birth and there is a death of that particular component. When does a component die? When it merges with another. Right? And in this context, we kill the younger one. Okay, so younger ones go away. The elder ones kind of continue. So it's called the elder rule, by the way. So you would have noticed that so B was born later, and so the component that was born here is younger. So when the 2 components merge at E, we let the component at A survive, and the component at B dies. So it has a there is a death event, right? And so this pair is what I call as a topological feature. So the component that was born at B ends, kind of dies at E, right? And the size of that feature to begin with is simply the difference in function value at B and E, right? So the height of that particular feature, right? So this is my topological feature and the size of this feature. Okay, so moving on to the question. So why do I know that these are actually the critical points? So this follows from Morse theory. I will not kind of describe the proofs and so on here, but essentially we all know what critical points are. Morse theory kind of studies critical points from a very interesting perspective, at least for me. So we know from calculus what critical points are. We know that the gradient should be 0, and we know about degeneracy and so on, right? We look at the Hessian. We know that there are in 2D there are 3 types of critical points, particularly kind of non-degenerate ones. You can classify them, for example, by looking at the number of negative eigenvalues of your Hessian. So the negative eigenvalues will capture the number of kind of descending directions. So for a minimum, this is 0, right? So the way I think about it, that's why it's intuitive for me, is I talk about this as in terms of stability, right? So if I'm at a minimum, how stable is that kind of critical point? So if I perturb, so if I think that I'm a drop of water and I perturb the drop of water away from a minimum, I flow back. So I'm stable along two directions, right? So how many directions am I unstable in, right? So that's what is captured by the number of negative eigenvalues. So I like this because that translates to a way to kind of classify critical points, right? So the key message here is that the number of negative eigenvalues of the Hessian tells me the type of critical point. Okay. So this is kind of formalized in Morse theory, which studies Morse functions. So the important kind of assumption in a Morse is that you always work with a smooth function, so at least twice differentiable, and we want none of its critical points to be degenerate, right? It's actually a fair assumption. So one of the fundamental results from Morse theory is the Morse lemma, which says the following. So you look at critical points. So we see three examples here of three different functions, and a minimum in one, a saddle in one, and a maximum in the other. Morse theory says that this is actually the behavior of any function, any Morse function in the neighborhood of a critical point. A very strong result, right? So it says that this is indeed the general behavior of any smooth function, a Morse function, right? So the Morse lemma more formally says that you can write f as x squared plus y squared, of course, subject to kind of local coordinates, right? And a local metric. Or you can write it as x squared minus y squared, a saddle, which is this, or negative x squared minus y squared, which is a maximum, right? So these three tell you the types of critical points, and so this is called index 0 critical point, index 1, and index 2, right? So this is something that's very useful for us in practice, because now I can talk about kind of applying this and identifying the critical points explicitly by looking at a local neighborhood. I don't have to do gradient computations and so on. It turns out that I can identify these critical points just locally, right? And for data in all dimensions, in fact. So the critical points, this requires a little bit more work. It's not just from Morse theory. There is work by, if those who are interested, I can give a reference by someone called Banchoff, who actually ported these techniques to the piecewise linear setting and showed that you can actually characterize critical points by looking at their local neighborhood. So what do I mean by piecewise linear functions? A function is never available to us in practice in its analytic form. We always have the function sampled at some points, and the domain is represented using a triangulation, right? So it's decomposed into a collection of triangles and tetrahedra and so on in high dimensions. So let's look at the 2D example here, just for illustration. We have a vertex V, and I want to classify it as minimum, maximum, or saddle. And this can be done, thanks to Banchoff, by just looking at the so-called link neighborhood, which is the set of vertices that are adjacent to me and the edges connecting them. Just by studying their topology, one can decide if I am a maximum, a minimum. You will see that the minimum has no points below. So the so-called lower link is empty. This has a lower link which looks like a sphere, and the saddle which has two components or more of the lower link, right? So this leads to an efficient algorithm for characterizing and locating critical points. And the size of the feature, this is referred to this is referred to as persistence, right? So there's a technical difference between persistence and what I'm saying, but this is essentially what persistence captures. The difference between the birth and death event, right? And that can be captured, like I said, by looking at the difference in function value between the saddle and the minimum that it's paired with, right? So if I know the size of the feature, I can use that to simplify my function, right? And that's what I can do here. So here, what we have done is I think there is some change. Okay. Right, I think there is some issue here. So let's ignore this for a bit, right? So let's just look at this particular case, because I think this refers to the super level sets. So just the sub level sets. If let's say this is the pair that I don't care about, right? What does simplification mean? It means if there is a way to fill that particular feature, right? Or if it's a basin, fill it up with water, right? And then that's essentially corresponds to removing that particular arc, right? So you can imagine that there is another function which is a simplified version of this function, where the only difference between the two being this particular feature is missing from the simplified version, right? And I don't have to think about the function anymore. This is just a tree, and I can just do leaf removal operations. Very simple computationally, right? So the merge tree allows me to simplify my function without actually applying any smoothing operators and so on, right? Yeah.
Vijay, but so there's an issue where you have to sample these functions at sufficiently many points to get a good representation, right? So there's something about the smoothness of the function and the number of sample points that you need.
Right. That's true. So for data analysis, we assume that the data is available at sufficiently high resolution to capture all the features of interest. We assume that that is already done, and we preserve that all the features that are captured in the sample. So we guarantee that if a critical point is preserved in the sample, then I will compute it and represent it in its true form. So I assume the simplest possible interpolation linear, and even with a linear interpolation, I'm able to capture the. Using this technique, but you would need some kind of understanding of the underlying model that or the underlying function. Without that, I don't know, right?
Is there some sort of a feature counting mechanism you can build that just from your output of the merge tree tells you, okay, this is just missing some features which should have been sampled?
Sure. So again, so let's say you are running a simulation and you know that within the Northeast region, right, I need to have twice as many criticalities as the Northwest, and if that doesn't happen here, then right, then you can identify, right? So all kinds of statistics can be performed on top of this because this is a combinatorial structure and it's amenable to all of them, right? So, but then that also assumes that you know a little bit about the underlying model or the application. Yeah. Right. I don't know how we are doing in terms of time. Maybe I'll quickly talk about the comparison and then talk about a few applications. So what we want is a way to compare two merge trees so that I can. So there are also several applications of a comparison, right? It allows me to look at time varying data to figure out if there is any significant change, right? It allows me to look at ensembles and so on, right? So there's several applications for looking at a comparison measure, but we want our measure to have some probable properties, while at the same time being amenable to computation. We don't want this to be kind of intractable, NP hard, and so on, right? And we want it to be understandable. We don't want just one number which is difficult to interpret, right? So these are our goals. And with that, we kind of introduced this measure called the tree distance for merge trees. For some of you, if you have worked with kind of strings and if you have seen edit distance, then this will look very familiar. Otherwise, I'll quickly go over the distance, and then I will talk about a few applications, right? So I have two trees. I want to find the distance between them. The main idea behind the design of this distance is, can I transform one tree into the other via a collection of edits, right? And I allow three kinds of edits. These edits are motivated by the fact that these are merge trees, okay? So I have, let's call lambda as the null or empty node in my tree. The first operation is an insert node, right? So where I have none, I have inserted a node q, okay? So this makes sense. This is inserting a feature, right? And you can imagine that a feature doesn't appear as a single node, it appears as a pair. So I will impose that constraint later, right? It always appears as a minimum saddle, right? So as two nodes. So we will impose that later. So, but insert is one operation. Since we have insert, we should definitely have a kind of a delete. So we have that naturally. In addition, we have a relabel. This is, imagine in your water filling, maybe the minimum is shifted up a little bit or shifted down a little bit, right? Or the saddle, the merging point is shifted up or down a little bit, right? So the label corresponds to this, the value, the scalar value at that node, right? So there is a relabel which allows me to go from one tree to the other by mapping one node here to another node, but with a change in function values, right? So very simple. These are the three operations that I allow. And I impose constraints on top of these operations, right? I allow for insertions only in pairs, like I said. So which means that I would like to preserve the property of the merge tree. So if I remove M2, I would also remove S1, right? Resulting in another merge tree. And similarly, if I remove M3, I remove it together with S2, resulting in another merge tree, right? I do not allow for subtree removals in general, right? This is something that is studied elsewhere, but I do not allow this because the resulting tree is not a merge tree anymore, right? It doesn't serve my purpose. So I do not allow such operations, right? The next comes the cost. What is the cost of each of these operations? This is where there are some ideas from this persistent homology that comes into play, but I'll try to introduce the kind of intuition behind the cost, right? You are inserting a feature. What is its cost, right? A quick way to see that is in this diagram called the persistence diagram, where the x-axis is the birth of a particular event and the y-axis represents the death, right? So Q is a node that I insert. Q represents a topological feature. It has a birth and a death, right? The feature that's represented by Q has a birth and death. And so that's a point in this space, right? The cost associated with inserting this Q is the cost associated with inserting this point inside this diagram, right? Points on the diagonal are where the birth equal to death. That's like nothing, so, right? So the cost is the cost of taking this point and moving it up, right? That is the cost associated with inserting a point, right? In this diagram, right? And for technical reasons, I look at the cost as half of that because it's split between Q and its pair. Q has a pair, so it's split, right? Deletion, the same thing. Cost is I take this point, I have what is the cost associated with pulling it back into the diagonal, right? That's the cost of delete. Now I think relabel would be easier to understand because I have PQ. I want to relabel P to Q. So P has a corresponding point here, Q has a corresponding point here. So the cost associated with relabeling P to Q is the cost associated with moving this point to here. Right? There are many ways to capture this. We capture this using the supremum. So essentially, we look at this cost, right? So you can see that here. So it's maximum of B Q minus BP dQ minus dP, right? But there is another way to move from P to Q, which is you just kill P and you just kind of create Q, right? So a delete and an insert. So that's also possible if that is cheaper, right? So we allow for that. So this diagram is called the persistence diagram, and there are some nice properties associated with this. Hence, we use it to kind of introduce everything. I did not introduce the theory behind it, but I'll be happy to talk about that later.
It must both work.
Yes, yeah, sure.
Even in the
Even in the relabel, yes. So you notice that this is, yeah, both, yeah, sure. Right, so that's the cost associated with all the operations. Now, if I give you two scalar functions, right, and the merge trees, remember that only certain operations are allowed. I can go from one tree to the other via a sequence of edit operations, right? So I first apply an insert, then a delete and relabel and so on, right? Some sequence E1 through EK, right? I have a cost associated with each edit operation, which is gamma of EI. I just add them up, right? And that's the cost of this sequence of edit operations E, right? That take me from T1 to T2, okay? And now I minimize over all possible sequences, right? So that is defined as the edit distance, right? Right, so the edits will, the sequence will be bounded, right? Because these are finite trees, so it will be bounded length. But yes, but the way I've stated it, there are several paths. Okay, yeah, so you could insert and delete and so on. So there are infinite paths. There are paths of length infinity, if you will, but I look only at finite paths. Yeah, sure. So this minimization is actually well defined. So okay, so that's where I will come. So I will talk about that quickly. Yeah. So in general, it's a hard problem. It's NP hard. So which is mostly true in many of these problems with correspondence, matching, and so on. But I just want to quickly say that. You remember, I wanted some nice properties. It's a measure, it's a distance, but it's actually indeed a metric. And the proof comes from the fact that one can show that each of these edit operations is a metric. And so you have a minimization over these metrics, so you can actually prove that it's a metric, right? So a lot of this work was done by Zhang, and our algorithm follows from Zhang, who looked at ordered trees and so on. So in the general case, this edit distance is NP hard to compute, but we look at what is called a constrained version, which is meaningful. So in addition to the edit operations that I talked about, I allow for only certain relabels. So so I'll just give a quick example instead of going into a detail because I want to talk about some applications. So if there are two nodes, one is an ancestor of another, right? I would like their relabel to also preserve this ancestor property. So I don't want two nodes, if one is an ancestor of another, I don't want the relabel to switch this property. This doesn't make sense for a merge tree. So adding this constraint turns out that the algorithm quickly becomes tractable, right? Because the search space reduces and there is a nice recursive formulation. And in computer science, we like recursive formulations, either because it immediately leads to a tractable algorithm, or you can throw space, and this is called dynamic programming, and there is a fast algorithm often, right? Yeah.
You are preserving this relation. It is the same as saying that you are, while relabeling, you are not changing the critical behavior at over things.
Okay, so we also ensure that is additional. That doesn't affect the runtime of the algorithm, but we do ensure that saddles are mapped only to saddles. Yeah, while relabeling. Yeah, that kind of follows quickly because the saddles are all internal. They are degree 3, and the minima are all degree 1. So it kind of is enforced in our algorithm. Yes, explicit, kind of implicitly enforced in our algorithm. Doesn't have to need doesn't need an explicit enforcement. Yeah, but that's an important point. Yeah, you don't want those kind of maps. So the running time turns out to be quadratic if you have degree bounded trees, right? So the rest is just dependent on the degree. So it's just quadratic. That's kind of nice. And it works fairly well in practice. There are versions of this that we have looked at, which study local subtrees. So I may have two trees which may look different, right? So the edit distance may be large between these two trees, right? So note that the geometric embedding of the tree doesn't matter for us. We are looking only at the nodes and so on, right? So these two trees may look different, but if you look at the subtrees, this subtree looks similar to this subtree. And I want to capture that often, right? And so we have a local version of this called LMTED, which allows you to efficiently compute this similarity, right? Okay. So a quick example to say how good this is, right? So here is here are three scalar fields just shown using contours, right? So you can imagine this is the global minimum. These are all maxima. There are 1, 2, 3, 4, 5, 6 maxima, right? And the greens, if you can't see, they are the saddles. So you can also see that using the contours, right? So you can notice that there are lots of similarities between the three scalar functions. There are some differences here, right? So this is the original, and this is just color coded to highlight the regions. So here is what the tree edit distance does, right? It gives you that correspondence between two trees, and as expected, the brown, which is this, is mapped to this brown, right? So those nodes are mapped, and the blue, everything is matched, right? So all good, right? So sanity check. But if you just do something simple, if I don't know if you have seen optimal transport, you must have seen, I mean, Wasserstein distance, some of you may have seen it. This is a nice way to compare distributions. So this is something from a Wasserstein distance, which is actually actively used in our community, in our literature, for finding similarities between two different distributions. Wasserstein does capture many of them, but it fails miserably, even in some simple cases. The reason is this. So this maximum is not matched with this. And the reason Wasserstein misses them is that there is a difference in the function range for these maxima, right? If you recall, what we do is we look at the function values. We also look at the tree structure, which captures this hierarchy, the nesting behavior. And that is very important, right? So that's what is crucial and is a is kind of an important advantage of the tree edit distance over Wasserstein. So it is able to capture this nesting behavior and hence say that these two guys are similar, right? And in this case, there are two kind of far away maxima, the brown and the pink, which are termed similar. So this correspondence is between these two, right? So it says that this maximum is similar to this. It seems possible, but then the nesting behavior clearly says that those two shouldn't be paired, and so the pairing is correct here. Okay. So there is a lot of interest in the tree edit distance because in addition to just comparing distributions, my edit distance is kind of sensitive to the geometry to some extent, right? While being efficient in practice. Okay, so from now on, essentially applications. One of the early applications of this edit distance was to identify repeating structures in scalar fields. Why repeating structures such as this? So you have two kind of legs in this heating kind of conductor, if you will, right? So this is the temperature distribution color map. I would like to find that M1 and M2 are the two symmetric copies. Because I call them symmetric copies because there is some transformation, I don't know what, some transformation that takes M1 to M2. In this case, it's a simple translation, but that transformation preserves the function values, right? So I would like to find all such copies. You can imagine quick scenarios where this is useful, right? Take a bridge and look at the stress distribution on all the piers and so on, right? The problem is difficult because we want to find all symmetric copies and we want to find it without explicitly specifying what is the transformation. That makes it a hard problem, right? And the answer comes from the tree. So I translate it into a simple tree comparison and solve it. But why do I care about symmetry? This is the figure I showed at the beginning. What I didn't show is that this is actually highly symmetric. This is actually the human adenovirus. This prior to SARS-CoV. So, and now this is something that everyone recognizes, something like this, right? With nice tentacle-like structures. So this is the adenovirus. It's a little bit different. So not the SARS-CoV, but also kind of plays a role in getting you cough and cold, I think. So this has dodecahedral symmetry that can be captured by just studying the tree. So symmetry appears in nature. Symmetry appears in proteins that build our human body. In fact, this symmetry is used. You have seen kind of the origins of kind of the DNA structure as right elucidation and the study of any protein structure. The symmetry actually helps solve for the structure. So so identifying symmetric copies is kind of a very useful kind of tool to have. Missing symmetry is also important. I think we used our tool to identify, so in this case, there is some simple kind of translation symmetry. We applied it on some codes and found there were some kind of some asymmetry, which turned out to be an incorrectly coded boundary condition. So, so it does help practically as well, right? Okay, so how do we find symmetry? This is exactly how. We look at, so let's say this is not the adenovirus, but this is the activated protein kinase. These are electron microscopy data. So you take the protein and it's kind of frozen and it's imaged. And what you see is that this has 3 units, right? Repeating units. Visually, that's what you see. But this is what we do. We compute for this data, we compute the merge tree, right? We look at all subtrees and compare them pairwise, okay? And this is the distance matrix for that pairwise comparison. Blue represents low values, red represents high values, right? So we quickly see that there are 3 subtrees that are nice copies of each other. And if you look at what those subtrees are, they correspond to these 3 big units, right? So here the rows are ordered in terms of the size of the tree, decreasing order, right? So the larger subtrees first. Okay? So you see the 3 copies here. Then there is a nice block of blue here, which corresponds to these smaller 6 repeating subunits, right? So the distance matrix just blindly applied on the merge tree allows you to capture these repeating kind of subunits, right? And this works for other larger data sets also. We did this using the local method, which doesn't require this additional step of finding all subtrees. It kind of solves that problem also. So here is a more complicated example with a lot of repeating units with rotational symmetry. This is the distance matrix. And just locating the regions around the diagonal, which are blue in color, right, dark blue. So that helps us identify the repeating units. There are 2 such that I've highlighted here. The first one corresponds to the larger kind of subunits that are repeating copies. So this is manually generated, by the way. The color and transparency is all manually kind of set up, right? This is kind of automatic, right? So where you compute the merge tree and you just let it go, right? So that's this. So kind of think of this as ground truth. Not really ground truth, but ground truth. Visualizations, ground truth. And then this is the result we have, right? And you can also identify other repeating units, which are not so clear even here, right? There are some other repeating units here, right, that we are able to identify. Okay. Okay. So a lot of this is put together into a kind of a base tool that we kind of released at that time. allowing people to quickly look at symmetric copies and then use that to study their structure, right? So I will kind of end by talking about something similar. I'm not talking about R4, sorry, but I'm talking about time-varying data, which is not the same as R4, but close enough, I think. So this is time-varying data. You can think about repeating units also in time, and this manifests in a different way as periodicity, right? And can we identify periodicity? That's the question, right? So this is a very simple kind of flow behind a cylinder that generates a von Karman vortex street. I don't have the video here. I know many of you may have done this. Those physicists would have done this. Please, this is an academic example, so excuse me, but then it clearly illustrates the point. So for those who don't know, the von Karman vortex street is this kind of street of vortices that form when you have flow behind a cylinder. So there is this vortex shedding phenomenon. And it's kind of a very interesting phenomenon because it's periodic. The vortices keep moving. And then if you compare the set of vortices in one time instance with the vortices a few time steps away, you will see that there is a nice periodicity and hence a street. What we show here is I think we use just the velocity here, and that's the magnitude of velocity, just speed, that's mapped to color. Okay, I think this is a little bit cleaner data set. Right. So we identify periodicity by just comparing the merge tree at one time step with subsequent time steps, right? And if you see the distance matrix, that's what you see, right? You see, of course, the diagonal is blue, but you see these off diagonals at 37, 74, and so on. So those are the, so in fact, we know that the periodicity is 74. We identify this other diagonal, 37, we call it half period. That's where the vortices kind of swap. So I think that's shown here. So you have the vortices here, right? You see that it's shifted a little bit, right? From here to here. This is 0, this is 0, this is 37. 0, this is 74. So 74 is a copy of 0, but 37 is something we call half period. We can't capture the geometric location, but it's the one where the vortices are swapped, right? Yeah.
Some interpolation in the time?
No, there is no interpolation. We are just computing. We have the scalar function at every time step in the simulation. So the simulation provides snapshots, right, of the velocity field.
Steps.
Oh, it's not a unit of time. It is the 74th time step.
But it may not come back to periodic thing, right? It might be that the periodic thing is actually in between the time steps. I'm just saying your time steps.
Good. Yeah, that's a good point. Yes, there may be some. Sure. So the distances here are not 0. They are a minimum, right? So I identify the closest 1 to 0. Yes.
Yeah, presumably you would have resolved your code.
Yeah.
To capture that small scale.
Yeah. I think I understand now.
This is the
Yeah.
It's literally copied.
Right. Yeah. Okay, I think from what I understand, this is after I think they let go of a few initial time steps. I think the initial time steps are where the vortices form. I think those are removed. Right. So yeah, until the flow. Okay. So thanks. Yeah. So yes, that's true. Right. So we also plot that. So you can see that the Wasserstein distance also does a decent job, but it's not as discriminative. So the green is the Wasserstein, So this is 0th time step compared with all other time steps, right? And you see that the tree distance is in blue. It shows this nice behavior and goes down close to 0. The Wasserstein, and there is a version of that called bottleneck, do a good job of capturing the periodicity, but they are not as discriminative in the sense that the function values for the tree editors is much clearer at distinguishing between what is similar and what is not similar, right? And hence, we would prefer the tree edit distance, right? This shows that with noise, you can get a cleaner picture with noise removal. After you kind of identify anything that's noise and remove it from the picture, the distance is much better.
Distance do with noise?
Okay, I think I have, yeah, so the Wasserstein will just reduce a little bit with noise. It's already fairly stable if you see. Yeah, so in this particular case, this is a very clean kind of data, yes, yeah. Okay, so you can do something similar to shape. This is more a graphics application. I won't spend much time. You have a bunch of shapes and I want to compare and identify which ones are similar, which are dissimilar. There is a way to do that using the trees. And this is a big problem in computer graphics. Because you want your queries to be processed quickly. Of course, naturally, you will see from the results, what is interesting is that you do capture the cats and the David dog and so on. All are different. They're all different boxes here, which means they are identified as different. But there are some off-diagonal blue, right, which is natural. The David and Michael, which are statues. So this is David and this is Michael. You would expect some similarity, but then they are different statues, so there is some reds here, right? Okay. So I will close with that. So what? Yeah. Question. Okay. Okay. So I'm happy to answer that. So okay. So this is a very interesting question. So here the question is, I don't have a scalar function. This is given to me, right? So all I'm given is the shape. So you can imagine your Kinect or some kind of a sensor will give you the points. That is the input that's usually given as input. What I want is a scalar function, scalar field on which I can compute the tree. So the scalar function shown here is called the average geodesic distance. So it's actually very related to PageRank. The PageRank, I don't know, Google uses something called the PageRank algorithm. This is heavily studied. I think even in heat diffusion and so on, it's more or less the same idea from what I understand. So the distance here is very simple. You take a point and the value of scalar at that particular point is the sum of distances to all other points. Okay. So geodesic distance, not Euclidean, geodesic, like on the surface, right? So you can imagine that if you are close to the fingertip, then the distance is very high compared to if you are at the center of the object. So this distance is able to capture protrusions very well. And hence it captures shape quite well. It captures the skeletal structure of the shape very well. Right.
I would have naively thought we should use some scalar curvature.
Oh, curvature. Yeah, curvature is very prone to noise. It just doesn't work. People tried it naturally. Yeah. You want some kind of a global measure here. Yes. Yeah. Thank you. Yeah, if someone's interested in shape, and I glossed over it, sorry, but this is very, yeah, something I really like. So. Okay. So yes, so here a crucial part of the application is designing that particular scalar function. And then things go kind of straightforward. Yeah.
Does it matter what kind of average for things?
Okay, so one good thing about the average geodesic distance is I can normalize it across all the shapes, right? By just, so I don't have to, so in that sense, I can be size invariant. So I have a small cat and a larger size cat in meters or whatever. It doesn't matter. I can scale it with the largest distance. So right. In that sense, this measure is scale invariant and also pose invariant. Pose. So this is the human body. This pose will also give you the same geodesic distance, right? So it's post invariant. So it's a very nice measure.
Is it, so you said about looking at noise and variance, right?
Yeah.
Let's say I have a sphere with noise.
Yeah, sure.
So like naively, because there's noise, I would assume the distances to be larger between the same thing because it's far.
Right. Goes. Yeah. Sure. Yeah.
You said this is noise and variance.
I said post invariant and scale invariant, but noise can be handled, by the way. So the kind of noise that you're talking about, it will appear as small arcs in my merge tree. If you have a lot of, if you have a sphere and you have a sphere with spikes, right? Imagine each of those small spikes, right? There is a local maximum on the corner of that spike, right? And where it meets the sphere, there will be a saddle. And I will pair that, and that will appear as a small arc in my merge tree, and I can remove that. So when I talked about this simplification, that's what I meant. I didn't explicitly talk about this. This epsilon is a percentage of, so if you take that arc and you compare its height with the range of your scalar function, this is that epsilon. Right? So even if I apply, so 0 is the same as that. Even if I apply 1.5%, right, I already get a very nice smooth curve. So the distance actually can be made robust to noise by explicitly applying this noise removal. Yeah. Okay. So I'll just summarize and then I'm happy to answer more questions. So what I meant to introduce is kind of two main points. One is how topology helps create visual abstractions and helps us at least generate feature-driven visualization techniques. Second, specifically, I talked about a comparison-based approach towards feature-directed visualization, and in that context, I introduced a distance measure. Right. So we talked about a TED for that, and which has a very intuitive cost model that's kind of motivated by the ideas from persistent homology. The algorithm is kind of fairly fast in practice. It supports fine-grained analysis, so I can compare substructures and so on very effectively using this technique, which is something nice to have. Lots of applications. I talked only about 2 or 3 here. We have other applications to the flow. There is extension to 3D. We have some applications to kind of more from biology and material science and so on. Right? So those are the 2 applications I showed today: symmetry and kind of summarization in time-varying data. The software we try to release so often. So all the software that's related to the edit distance is available, or it will be made available soon. One version will be made available soon. That's all available from our lab page, and descriptions of these methods and the results that I talked about today, they are all available in videos. You can look at the YouTube. MTED and LMTED will be made open source within a month. Yeah, the other softwares prior to that are already available. Yeah, the 2 distance measures will be made available soon. The paper is already accepted. We are submitting it for review. As soon as that review is done, we will be releasing it. Yeah. So the YouTube channel shows other things. So of course, there are lots of things to do in future. There are other graphs that capture the geometry even better than the merge tree, of course, at a cost, computational cost. Something called the extremum graph, which captures the maxima and their neighboring behavior, right? So we are currently working on distances between these so-called extremum graphs. And now we have graphs, no longer trees, so that kind of makes it a more difficult problem to solve. Right? There are many other such problems within this space. and also in terms of applications. Thanks very much. Much of what I discussed today is work by Raghavendra, including some of the pictures which he generated from his applications. So thanks to him, he's graduated now. That's Raghavendra, and he's doing a postdoc. Thanks to all the funding, and thanks for all the questions. I'm happy to answer more. So I'll end my talk here.
Say if you have a vector field where like multiple scalars have some relationship between
Yes.
them, how would you modify this, or what modifications?
Right. So I would think vector fields as slightly different from multiple, like multi-field, because there are some natural kind of meanings associated with the vector field. So techniques like Morse theory have been kind of extended to the study of vector fields. So one can talk about these so-called invariant sets, so which correspond to critical points and their regions, right? And there is similar to the merge tree, there are other these connecting structures that have been computed for vector fields that help decompose your entire vector field into regions with some kind of streamlined behavior. So there is some study there. That hasn't yet been translated into comparison measures, but this is in our community is called vector field topology. So it has been studied, and a lot of focus there is how do you avoid the problems with numerical integration. I said avoid. I didn't say do it better. So the ideas there are, how do you make this into a discrete combinatorial problem while providing some guarantees and doing your computation? So, and that have been fairly successful. There are some combinatorial versions of vector fields, and people have computed these topological structures on them. Track, for example, vortices over time and so on. Yeah, there's a lot of very interesting work. Vector field topology is what I would get. TDA, yeah. TDA, topological data analysis.
Distance.
Oh, distance, TED, yeah, treated distance.
Has this been used in any of these ML-based programs where they need a loss function to identify features?
Yeah.
Because it sounds like that's what you're sort of doing. You're identifying some features and transforming from one topology to other by making this change of features under certain rules of this merge tree.
Yeah.
For distance T. And can this be used?
Correct. No, it's a very good question. There are several other distances defined between trees, and they are slowly in the pipeline. So not yet incorporated into an existing ML pipeline. But there are, I didn't talk about other distances. There are, I think for trees, there are now about 6 or 7. Not all edit-based. We introduced the edit-based initially. Now, following us, there are a few more edit-based measures. There are a few which are based on optimal transport. There are others, completely different approaches. The key is to, so yes, the idea is to incorporate them into a ML pipeline eventually. Not our goal. Our focus is more on visualization. So, which is why one of my goals is interpretability. Can I understand this measure? Right? So that is my goal. But there are others who are looking at incorporating such measures into a ML pipeline. One key problem that they have to solve is they will have to vectorize the tree somehow if they want to incorporate the tree also into their pipeline. Right. So most of these existing ML pipelines, the current ones, there are new ones using that work on graphs, but all the big pipelines available are for images and 3D volumes. So they need you to vectorize your input somehow. As in some long list, right? So vector. So that is the key. How do I do that? Yeah, but there's a lot of work. Nothing from our group.
Okay, given time, maybe we'll close the session. I'm sure Vijay will take questions offline.
I'm happy to. Yeah.
People can email him. All right, let's thank our speaker again.
Thank you. Thank you. Thank you for saying that.